All right, so next week you'll have your midterm in this class. So it's going to be composed of two parts. The first part is going to be written. You're going to get your papers and write your answers on it. You will also see the programming question. But before starting to work on the programming part, you need to turn in the written exam. And then you'll open your computers and start working on the programming questions. The programming questions are going to be very similar to the problems that you've been working on. And you can look at the sample midterm. Two of the problems that are due next week are from the past midterm. Solutions are already available on the web. Make sure to just on time before the midterm, even though they are due after the midterm, you should be finishing them before then. All right. You can study the solutions and listen to the recorded lectures for the midterm. But when it comes to solving and submitting your answers, you need to make sure that you don't copy and paste from the provided solution. Rewrite yourself. Okay, so I'm going to go over these midterm questions from last year, from last quarter, and solve them one by one. So in the first problem, you are asked to convert, you're asked to reverse the elements in A. So if the vector A contains 3, 7, 2, 9, you just need to reverse the numbers and have them go 9, 2, 7, 3. You're not really sorting the numbers, you're just reversing the order of the elements. So the first one will become the last element, the last one will become the first element. We need to think about this problem in terms of selecting elements of the vector A. If A is a vector like this, you are trying to generate a new vector where you are selecting the last one first, second from the last, and so on. Okay. So you need to think about the indices of the elements that you are receiving. Okay. So the last one is going to have the index 1. And the first element is going to have the index. If the number of elements is n, it can have the index n. But you are asked to write a single statement. You don't have the luxury of saying n equals number of elements in A. All right. Instead of n, you can alternatively use the keyword END. But let's use n for now, and then I'll replace it with END. So you need to generate this index vector that you are trying to select from A. So that's going to be n minus 1, n minus 2, all the way to 1. You say A. This will give you the elements of A in reverse order. You are referring to the nth element, n minus first element, and so on. Okay? A shorthand to generate this vector is to just say n all the way to 1. If you omit the step size, this will generate an empty vector. Right? If you say 5 all the way to 1, you are starting from 1, going up 1 by 1, 5, 6, 7, you will never get to 1. So this will result in an empty vector. You need to make sure that you have a minus 1 here. So you start from n, go by minus 1 until you get to 1. So the answer is A. You no longer need the square brackets. You're going to use the keyword END. Minus 1, 1. So I'm generating the index vector first, which helps pick out the elements from A. All right. If you don't like using the keyword END and really are insistent on using the numal function, you can replace that with numal function, numal A minus 1, 1. So it's still a single element, a single statement. All right. Any questions? Okay. The second problem is, again, using these the colon operator to generate vectors that contain numbers that have a certain step size, and also two commonly used functions called reshape and refmat, which you use in some of your homework problems. And you concatenate different vectors using square brackets. So when you have square brackets, you are just taking all of the inside vectors and putting them together to generate one big vector. And since I don't have semicolons separating these different elements, it'll just be one single row vector and not a matrix with multiple rows. So let's look at each of these individual vectors. 3, 1 will be an empty vector, right? You start from 3, you try to go all the way up to 1. You will never get to 1 if you go with a step size of +1. So if you had 3 minus 1, this would have generated 3, 2, 1. But since we are missing this minus 1, this will give an empty vector. So the first part is not contributing anything to our larger vector. The second part, we start from 6 with a step size of 1 all the way up to 4. Again, we'll never get to 4. We are going up, right? Starting from 6. This will also give an empty vector. It does not contribute any numbers to our larger vector. The third element is 9 with a step size of -2 all the way to 7. So we'll start from 9 with a step size of -2. We get to 7. With another -2, we get to 5. We are already past 7. This will be the resulting vector. So this expression contributes two numbers to the overall vector. So let's write those down, 9 and 7. Okay. So far we have two numbers in our overall vector. The last element contains this reshape and refmat expression. We have a function called, you need to evaluate its argument first. So we'll evaluate the result of the refmat first, find what its output is, and then give that output to the reshape function to get another output. The refmat function takes a block of a matrix. It could be a single number, it could be a row vector or a column vector. And you have to think about that block of matrix as a black box. And you just replicate it as many number of times along the row as specified by the first argument. Sorry, this is Tn1. So we'll replicate it 3 times along the row, and 1 time along the column. So we'll take our black box, we'll make 3 copies along the row. So including itself, it'll have 3 copies. And along the columns, we'll have just a single copy, which means we are not replicating. Okay, so we'll just have it by itself. Whatever that block is, in this case 1 and 3, we just create 3 copies along the rows. 1, 3, 1, 3, 1, 3. And as a result, we are getting a matrix that has 3 rows and columns. All right, so we get a matrix that contains 1, 3, 1, 3, 1, 3. That's the result of the refmat. So you can take this refmat expression and replace it with this matrix. Okay. Now we get to the reshape function. Reshape function takes a matrix and you change the dimensions of that matrix. This matrix initially contains 3 rows and 2 columns. We want to generate a new matrix that contains 1 row, and you are asking MATLAB to figure out the number of columns itself. Keeping the number of elements the same, you are just reshaping the matrix. And when you are reshaping, you are not changing the order of elements as you would see them in the linear order. So they will still have the same linear order, but the number of rows and number of columns will be different. So I'm going to take this matrix and rewrite it on a single row. So you have 6 elements, you need to have 6 columns, 3, 4, 5, 6. The order of elements in linear indexing will not change. So you go down the first column first, 1, 1, 1, and then second column, 3, 3, 3. This may be sort of counterintuitive to how you would see this matrix printed. You may think that you would have 1, 3, 1, 3, 1, 3, but MATLAB uses column in that column order, which means you have to go down the first column first and then the second column. So if this, let's call this matrix A, this matrix B, A linearized is the same as B linearized. These two are going to give you the same matrix, the same vector. All right. So now we have this vector resulting from the reshape function. So we can replace this expression, result. We had 9, 7 in our overall vector, and we'll additionally have 1, 1, 1, 3, 3, 3. And that's the answer. The next problem is testing your knowledge of the variable scope, which means that every function has their own variable. The fact that the names are the same in different functions is just misleading. The variable a in one function has nothing to do with the variable a in another function. You may use them to semantically refer to the same information, but as far as their coding goes, as far as MATLAB is concerned, they are different variables. And the only way they can be related to each other would be by passing arguments in order such that they correspond to each other. So one way to make it easier is to take a function and find all occurrences of a variable name and replace it with something else. So this function will behave in the same way if you took all of the variable a's and replace them with, let's say, apple, or we already have something. Let's replace them with x. But you have to consistently replace everything. I'm replacing variable b with y. Okay. So this will make it easier for you, so you don't confuse the variables in this function with the variables in the command window workspace. So we'll go step by step. Variable a is assigned 5. So you have a box called a in the command window workspace, and you store 5 in it. All right. So this, you took care of this expression. In the next line, you call apple function with the value of a, which means you just look up this number 5, you extract it, and you pass it on to this apple x variable. So as soon as you get into apple function, you are creating a variable x and putting value 5 in it. Let's go through the next line of code. X equals x times 2. You take 5, you multiply it by 2, you get 10, and you store it back into x. That makes it 10. And then you take x, you multiply it by 3, which gives you 30. You store it in a new variable called y. and you return y. So the value 30 is being returned from this function. And it's stored into the variable b. You are creating a variable b and storing the value 30 in it. In the next, okay, a is 5 and b is 30 at this point. And in the next line, you are calling the apple function with the number 7. So a is 5, b is 7. And I don't even need to bother taking this number, going to the apple function and calculating the output, because I'm not really doing anything with that output. Yes. Sorry, b was 30. My bad. Yes. Okay, so b is 30, it's not 7. When you call apple with 7, this it's going to be passed on to this variable, and then you're going to do these calculations and return that value of p, which is not really stored in anything, so you don't have equals to something. So you are calling a function but not doing anything with its output. You can ignore that line. So just pretend that that line does not exist as far as the variables a and b are concerned. Okay. And in the last line, you create a vector AB. So it will contain 5 and 30. Remember, the square brackets just put together whatever is inside of them. So you're generating a larger vector that contains 5 and 30. And there's no semicolon at the end of it. MATLAB will print results, so you'll get 5, 30. So the answer to this problem is 5 and 30 printed in the command window. There's a question? Yes? Okay, so if the question is, if I call Apple 7, since there's a semicolon at the end of it, ANS variable will not be created. So let's test this. So since I'm sort of not showing you the workspace, whose function is it's a function that will list the current workspace. So if I say a equals 5, and then say whose, it'll list me the variables that are present in this workspace. If you make a calculation, let's say 6 plus 5, and you have a semicolon at the end of it, it does create the ANS variable. Actually, no. It does not create the ANS variable. This ANS is from the previous a equals, hold on, what's going on? Let me clear again and start over. Maybe I should show the window. Okay, this will make it easier. So let's do 6 plus 5 with a semicolon. It does create an ANS variable with the value 11. So you are right. Even though we are not capturing the output, it's creating a special variable named ANS. But in the next line, that variable is overridden. Okay? So you still don't need to care. You still don't care what the result of this function call is. All right. So the answer to this is 5 and 30. In the next problem, you are asked to convert between row and column in this indexing to. You are asked to convert from linear indexing to row and column indexing. So you are given a matrix that has 100 rows and 1 million columns. And in that matrix, there's the 2468 element, and you're asked to find what row and column number that corresponds to. So again, you'll use linear indexing. There's a formula to help you go from one to the other, but you don't need to memorize the formula. You can just look at the matrix yourself. So since the matrix has 100 rows, the first column will go all the way to 100. The second column is going to go all the way to 200. And you have 1 million such 1 million columns in the matrix. All right. So it starts from 1. An easy way to do this is to pretend that numbers start from 0. And this is explained in the lecture notes. You can refer back to the lecture notes on why this makes more sense. So I'll just subtract 1 from 2,468. You get 2,467. And you divide it by the number of rows, 100. So this tells you how many complete column blocks you need to go through. Okay? So the answer is 24, and there's 67 remaining. Right? But because we subtracted 1, now we need to add back 1. Okay? All right, so this will be plus 1. So you have you are at 25th row and 68th column. 25. Okay. Let's verify this. 25. So let's go the other way around. We are given the row and column index 25 and 68, and we want to find the linear index of this of these row and column indexes. So the first row goes all the way to 100. The second row goes all the way to 200. The second column. The 68th column. No, I need to reverse these. No, the 25th column. Hold on. This is not right. I just the rows and columns need to be reversed because I'll just show you going the other way, and you'll see why. So if I go all the way up to the 25th column, the numbers have to go all the way to 2,500, right? So the last number in the 25th column is 2,500. The first number in the 25th column is 2,401. 2,401. The index of this element is 2,400. Okay, makes sense? All right, so you start from the 2,400 and first element, go down 68 rows, and you get to 24. Okay. So you can go the other way to make sure that you have the correct answer. So the answer to this is 68 and 25. Right. Any questions? All right, so in this problem, we are given a matrix with 3 columns. and we don't really care how many rows it has. The code that you write has to work for a matrix that has any number of rows. And we want to select from M such that we only keep the rows where the first column is smaller than the second column, and where the last column is the product of the first two columns. So we have two conditions. We want to select the rows of M that satisfy these two conditions. One way to solve this problem, if I didn't tell you to use vectorizing code, would be to use loops. Okay, but the question is specifically asking you to not use loops. If you were to use loops, what you would do is just say for I equals 1 to the number of rows in M, and then check if first column is smaller than the second column, and the last column, M3, is double equal the product of the first two columns, M1 multiplied by M2. And if this is the case, then you would, let's say, RET is another variable. You would add to the end of RET n plus 1, comma, we write it more neatly, n plus 1, comma, colon equals, I is here since I'm referring to I row. I comma 3, and so on. Okay, so this would be I comma 4. E and D, E and D. So I'm going through each row. If the first number in that row is smaller than the second number on that row, and the third number on that row is the multiplication of the first two numbers, then I'm creating a new matrix by copying that row into that new matrix, to the end of that new matrix. I want to do this in sort of one line of code without using loops. To do that, you need to generate a logical vector, okay, that will contain true for the rows that satisfy these conditions. So M is a matrix. M. Let me call the logical vector that I'm creating to be I. If I say M colon comma 1, this will refer to just this entire first column. So I get a slice, a vector of matrix M. And I say that this is smaller than M colon comma 2. This expression is extracting the second column. And when I say smaller than, you are comparing those two columns, those two vectors, and you will get a logical vector as a result that contains true wherever the first element, the first row is smaller than the second row. Okay, so that's the first part. We just put this into parentheses just to make it easier for you. All right, so what we'll do is we're going to take this vector and end it. Now I'm using a single end because I want to do element-wise ending. When you use double end, it only works for two single numbers. If you want to take two vectors and apply AND operation for each element, then you need to use a single AND. All right, so I am doing AND. Now if you write my next expression, which will take I'm just going to move on to the next line, which will take the third column. Okay, so I'm taking the third column and saying equal to the first column multiplied by second column. And I have to make sure that I'm using a dot multiply if I want to element-wise multiply the two vectors. So this gives you a vector. This gives you a vector of the multiplications of the first two columns. And you're just checking whether the elements in those two vectors are equal to each other. So again, you will get a logical vector where you have a true whenever this condition is met. Okay. Let's put it in parentheses so we don't confuse the order of operations. So now I have two parts to this end that contain the two conditions that I want to satisfy. Both of these are logical vectors, and when you add them together, as a result, you will get a new logical vector that will contain true only when both conditions are met. And what you will do is take this I, you can store it in a new variable by saying I equals, and then in the next step, you can use I to select the rows of M. And you are still picking up all columns. We are not doing any selection on the columns. We want all three columns. Okay? But we only want to select the rows that have true for these two conditions. Okay? All right. And then what we also want to do is change M itself. So we want M to be this new matrix where these conditions are met. Then we just need to say M equals. So the answer to this problem is to first say I equals this expression, and then to say M equals M sub I comma column. Right. Any questions? Yeah.
So for the first part, the logical vector you get out is two columns,
No, the first, so this let me highlight it. Are you asking if this part has two columns? No, this part has one column. It's a one column vector. So what you do is you take M colon comma 1. That is just the first column of the matrix M, right? And then you compare it with the second column. And when you compare two numbers, you get a single number out, right? When you compare two columns, you'll get a single column as a result. So we just go to MATLAB, create A equals 4080. Let me transpose so it's a column, all right? Let me say B equals 4600. So these are two column vectors. And when you say A and B, you're ending these two together. As a result, you will get a new a logical vector that's a single column. And for each position, it will contain true only if at that position A and B were non-zero. And you could do A smaller than B. Again, you will get a single logical vector where at that position A is smaller than B. Okay, in the last written part problem, you have nested loops. So what nested loops are, you just have a loop within another loop. You just need to think about one loop, keep track of its variable for each of the values that its loop variable will take, and then move into the inside loop and run that for each of the values it will take. And usually, in some cases, the inside loop variable will depend on the outside loop variable. just like in the problem where you had to number of times that in a matrix an element in the lower triangle was smaller than an element in the upper triangle. Instead of going through the entire row within all of the columns in each row, I described to you that you could go only up to the diagonal. Right? For each row, you wanted to go up to the diagonal. So you only wanted to travel or traverse these elements in your matrix. Okay. So for the first row, you didn't really go through any columns. For the second row, you only went through the first column. And for the third row, you went through the first two columns. So the number of columns that you went through depended on which row you were processing. And in that case, what we had was for I equals 1 to number of rows, and for j equals 1 to I minus 1. So the number of columns that you go through depended on which row you were currently on. If you wanted to go through the entire matrix, then it was you would have to replace that with the number of columns. All right. So this problem is similar. We have two variables A and B. The inside loop has the B variable that depends on the values of the outside loop. And this problem also has an indentation issue, meaning the loops are not on different lines, but you should still be able to separate them and think about them separately. So let me rewrite these loops for A equals 1 and 2. So I'm then going to run this outside loop for A equals 1, and then when it's done, I'm going to rerun it for A equals 2. Inside loop has for B equals A plus 1 all the way to A plus 2. So I don't know yet until I run the outside loop what the values of A will be for each iteration. For the first iteration, it will be 1, and you need to calculate this on the fly. So when I get to that point, then I will know which values B will take. Now for each of the iterations of the inner loop, I perform this operation, which takes A and B and stores it as a new column in X. So X initially contains 2 rows and 0 columns, so it's just was an empty matrix. But you are committed to store 2 rows in it. If you say size of X at that point, you'll get 2 zeros. Right? So it contains 2 rows and 0 columns. So why is this more convenient than saying a 0 by 0 matrix? It's convenient because you can say things like X colon comma something, and this comma will know that it's 1 through 2. So this will be replaced with 1 and 2. Okay, or if you have an END keyword, it will be replaced with 2. That's the difference from having a completely empty matrix with 0 and 0 dimensions. Okay, so let's go through the outer loop. A will be 1. Let's create a variable A, store 1 in it. And I will also write the values that A will take, 1 and 2. So I'm processing 1 first. I move into the inner loop, which creates a variable B. that will take on values a plus 1 all the way to a plus 2. The value of a is 1, so b will go through 2 to 3. The first element is 2, and then I move into the inside of that loop. I run this expression that says x colon comma e and b plus 1 equals 1, the value of a, and the value of b, the current value of a and the current value of b. Okay? And this e and d will be replaced with the number of columns in x at that point, which is 0. So this is the same as saying x colon comma 1. The colon will be replaced with 1 through number of rows in x. So that will be replaced with 1, 2. So in x, on the first row and the second row, and on the first column, we are going to store these two new numbers. So x is this. You just extended it by one column and stored 1 and 3. Okay. So now the inner loop is done. So this 2 is done. The next number is 3. And we are going to run the same statement for b equals 3. A is still 1. So what we do is run the same expression, but now this vector is 1 and 3. X colon is going to be replaced with 1 and 2 again. The E and D keyword will now be replaced with 1 because we have one column in X. 1 plus 1 is 2. So what happens is you are saying X 1, 2, the first 2 rows, comma 2, the second column. So that just extends X to move on to the second column, and you store 1 and 3 in it. So at each run of this expression, you are extending X with one more column. Okay, so now we are done with b equals 3. The b loop does not have any more numbers to go through, so that's done. We can go back to the top of the outer loop, the a loop, and get the next value we can do. All right, now we are back in the inner loop. B equals a plus 1 all the way to a plus 2. That will be 2 colon 3. Now we're going to go through numbers 3 and 4 for the B loop. We take 3, we extend X for 2 and 3. 3 is done. We take 4, we extend X with 2 and 4. B equals 4 is done. We go back to the top loop, the A loop. There are no more numbers to go through. The A loop is also done. And we are done with this, with these two for loops. We are just displaying the values of X, which will be this matrix, 1, 2, 1, 3, 2, 3, 2, 4. So the answer is going to be 1, 2, 1, 3, 2, 3, 2, 4. Okay? All right. This is, there are more complicated examples in the previous practice midterms that you can go through. All right. So let's take a short break and then I'll go over this programming problem. So let me just start with the programming question now. We are writing a program that makes a simulation, and this is a very common task in let's say systems biology, where you have a system and you want to know how it will behave in different situations. And what you sometimes do is take an example scenario and simulate it over time, make changes as defined by a set of rules and see what the outcome is going to be. So in this problem, we have a simplification of a biological problem. In real life, the scenario is going to be different. You have to make some simplifications, some assumptions to model the problem and then simulate it. We are given a tube that is of length L inches, and we are considering each inch segment separately. In MATLAB, we're going to use a different number for each inch of this tube. We have ants placed in this tube, and they can move freely. And we want to simulate this over time. What will happen after 1 minute? And at each minute, after each minute, if you look at any segment and look at the ants in that segment, half of them are going to move right and the other half are going to move to the left. Okay? So that's one step. Half of them are going to end up here, the other half are going to end up there. And since this is a simplification, you should not worry yourself about ants being in the middle, or having half an ant. So half an ant, even though it's unreasonable in real life, we will consider it feasible in our program. So there will be such a thing as half an ant when you are doing a calculation. As an example, let's take this tube that contains just 3 segments. So the tube is 3 inches. There are 3 ends here and 0 ends in the neighboring cells. After 1 minute, 1.5 of these ends move to the right, and 1.5 of them move to the left. So we end up with 1.5, 0, 1.5. All right? That's the answer. If you start with 3, 0, 3, at the ends, I'm going to try to move left, but they can't, so they remain where they are. That's 1.5, will stay where they are. 1.5 are going to move to the right, and similarly 1.5 are going to try to move to the right. They can't, they're going to stay where they are. Actually, in this problem, we get rid of them. So let me take that back. 1.5 are going to fall off the tube. 1.5 are going to fall off the tube from that side, and the other half are going to meet in the middle. We'll end up with 0, 3, 0. All right. So you need to read the problem that will describe these extreme cases also, and your code needs to handle these extreme cases. Yes. Oh, it does. I didn't look at it very carefully. All right. Thank you for warning. I thought I saw zeros in there. So let's go back again. So the ants don't fall off. I just wasn't looking at these numbers carefully. So 1.5 stay here, 1.5 stay here. And then we end up with 1.5, 3. Thank you for correcting. Any questions about the problem? So we can write a for loop to solve this problem. You can certainly solve it also without for loop, but using for loop is going to make it easier. What we'll do is we're going to go through each of these cells one by one. We're going to have a vector that contains the ends in the original state. And we're going to generate a new vector that contains the next time step after 1 minute. we're gonna move ends one step to the right and one step to the left. We just start writing the code and hopefully it'll make more sense. I'm gonna make some errors initially. No, I'll track them. So if I take the v sub I, that is the number of ends in the I box. If I divide that by 2, that's the number of ends that I need to move to the right and to the left. Let me initialize my output vector to be the same size as v, but containing 0. So whatever red sub I contains, I'm going to add, sorry, to the left means I need to look at the -1. I'm copying half of the ends from v sub I to red I minus 1. So in my for loop, if I'm currently here, in the v vector, I need to copy half of the ends to the I minus 1 location in the red vector. And the other half are going to go into I plus first location. Make sense? All right. Initially, red contains 0. As I go along the entire vector, it'll contain ends coming from both sides. I'll go over this and go step by step after I write the code, and you'll see how the vector change. Equals. So we'll do the same thing for red I plus 1. So half the ends move to the left, half the ends move to the right. And that will solve the problem, but it will introduce some problems, some errors that we need to resolve. And those errors are the boundary cases. So when I equals 1, that's when I'm looking at the leftmost box. I cannot move left. Right? So this expression is not going to be valid. This expression is not going to be valid. So I have to say if I equals to 1, then I need to do something else. I need to do red I equals the I divided by 1. So half the ends stay where they are. Okay? I'm adding them to the current location. Else, I move them to the left. So for the leftmost box, for the first box, I move them to the left. Sorry, I keep them where they are. For others, I move them to the left. You can also replace this I with 1. At that point, you already know that I equals 1. So it will give you the same result. Okay. And similarly, I just check for the rightmost box. If I equals the number of elements in V, then I cannot move to the right anymore. I have to keep those ends where they are. Else, I move them to the right. Okay. And that should solve the problem. use and 0, 3, 0. We get the correct answer. 3, 0, 3, we get the correct answer. So just a single box, the answer doesn't change. They cannot move to the right or to the left. If you have an empty vector, you get an empty vector. So you can test these cases that may or may not be described in the problem. Check another one. 2, 2, 2, 2. It says that's good.
If you're at one, why does it also move
If I am in the first box, half the ends cannot move left, but the other half does move to the right.
right?
The ends moving to the right. So this looks at it from the point of coming into a box, not moving out. Actually, let me rephrase that. No, it does look at it from the perspective of taking the ends and moving them into the picture box. So when I equals 1, okay, you move them, you keep them where they are, right? And at this statement, when I is 1, assuming your vector is larger than 1, you move them to the right. Okay, so this part is the part for moving to the left. That part is for moving to the right. And for moving left, if you are in the first box, you keep them where they are. Otherwise, you move them to the left. For moving to the right, if it's the last box, you keep them where they are. If not, you move them to the right. If you are in a box that's neither the first or the last, then for I equals that box, you would be running the else statement. Yeah, so you will move half of them to the right and half of them to the left. Okay? Make sense? All right. Yes. On which value? All right, so a common mistake that you may fall into when solving this problem is replacing the vector v itself instead of creating a new vector ret. So let's see what happens then. Let's return v itself. Just then rename everything with v. Okay. So you may be tempted to write your code this way, which operates on the vector itself. All right, so what you would be thinking of doing is for any box, taking them to the right, to the left and to the right and changing that vector itself. But when you do that, what you are ignoring is that as soon as you change it, you've changed your original vector, and the ends in the neighboring cells are no longer the same as original. So moving these guys to the left and right will be using your those added ends instead of the original number. Okay. So this code is not going to give you the correct answer. Okay, so can we solve this problem without formulas? Can you guys think of any way to solve this without formulas? Any ideas? Okay, so let's think about this problem. You have a vector, and you just move it to the right. Okay, so let's just have this reference line. If I just move it to the right, So it aligns over here. Okay, and then I will move it to the left. So it aligns like this. And let's let this new vector be half of the original one. So it'll just be the same values, but half, but also shift to the right. And the other one's going to be shifted to the left. And if I add these two up, the green and the red, it should give me the number of ants in the new vector. Right? So let this be v, and this one v divided by 2, but shifted to the right. This one v divided by 2, but shifted to the left. And when I add them up, when I add those two parts up, this number and that number, it'll give me the number of ants in the second box. This one will be the first box. And then I'll have to worry about the ants, and I can just fold these back onto the ones before, the preceding boxes. Okay? All right, so let's solve it without loops now. I'll take vector v and divide it by 2. Let's just say v equals v divided by 2 for simplicity. So now the vector v contains half the ants. Shifting to the right would just be v 0v. Okay, so that I'm just adding a 0 at the beginning. Shifting to the left is not really obvious. So what I'll do instead is shift the other one by 2 places. And then v is going to be, relatively speaking, it's going to be moved to the left by 1. Okay. So this is one vector, this is the other one. Make sense? No. Okay, so let me describe it this way. I took my vector v, which now contains half the values, and I added 0, 0 to the beginning. 0. Then I made another copy. I created a new vector that contains the v itself, and then 2 zeros at the end. Now, does it make more sense? Okay. Because moving to the left would mean that I'm dropping one of the values, and I don't really want to drop it. Okay, so I do want to keep the value in that box. So you don't want to, you cannot say v minus first element or v zeroth element, right? The indexes have to start with 1, so that's why you can't really directly move to the left, but you can make it so that relatively speaking, relative to the other vector that you generated, it's 1 to the left. Okay. All right, so your original vector would be here. Now I'm speaking relative to this vector. Okay. And having 2 zeros at the beginning and having 2 zeros at the end just make it easier to code. All right. Are we good? Okay. So now if I add these two vectors up, I'm going to get the answer, but except that I have to fold in the ends into the matrix itself. So let's just change V itself. That now contains the two halves, move to the right, move to the left, and add it together. So now at this point, V contains the answer with two additional boxes on each end. So I'm going to say V2 equals V1 plus V2 plus V1. So I took V1, added it to the second box. Let me draw those boxes again. Actually, let me finish this and then I'll draw the box and show you what happens. All right, so I had this vector V, which is the half of the original vector, and two zeros added at the beginning. And I had another one, two zeros added at the end. I add those two up, and I get this new vector that contains this additional box I need to get rid of, this additional box I need to get rid of. And the way I'm getting rid of them is I'm adding the first one into the second one. I'm adding the last one into the second from the last one. Okay. Now that I've sort of added them into where they are supposed to be, I can shorten my vector and ignore that first entry and the last one. So this is one way of doing it. Another way of doing it would be to say empty vector v1 is equal to empty vector. So I'm removing the last box, I'm removing the first box, which can equally be written as selecting second through second from the last box. Okay. So let's see if this works also. It should give the same answer. All right. Any questions? All right. So this problem, it works for one dimension. Right? So you should be able to solve the same problem for two dimensions. So if you think about a checkerboard and you are asked to move ants around, and you may be given different rules, then I guess one for them would have to move up, one for them would have to move left, right, and down. You can solve it using nested for loops, where you would go through rows and columns, or you can use linear, or you can use code without using code. But then you would have to pad your matrix by two rows and two columns. So the boundary conditions for this problem was that the ends on the ends don't move out; they stay where they are. If you are given a different boundary conditions where they fall out off the board or off the tubes, you should still be able to put that in. So if you were to have the ends fall off the board, fall off the tube, what you would do that is to just ignore these two lines. They'll make it so that you are not adding them into the previous boxes or the next box. You're just ignoring those two boxes by eliminating them from your vector. Any questions? All right. Any questions for this week's or next week's homework? Yes. If you are Okay, so how do I give default arguments? Right? Is that the question? Okay. So let's say I want to be able to call diffuse ends and not provide a vector. And in that case, I want the function to test it for 0, 3, 0. Just an example, just a sample input. There's a function called exist that, among other things, checks whether a variable exists in the current workspace. A variable with a certain name. So does the variable A exist in this workspace? Yes, it does. Does variable Apple exist in this workspace? No, it doesn't. If you don't pass a value for V, at this point right here, the variable V will not exist. And as soon as you try to use it, when you say V divided by 2, you will get an error saying that not enough input arguments, you are expecting V to be there, but it's not there. What we need to do is here say if does not exist a variable named V, then set V to be something. And you can V is not given. Okay. So that if statement will be executed and V will contain this. There's another way to get optional input arguments, and that's by saying var argument. So that stands for variable number of input arguments, or variable input argument. Variable argument input. But that's a cell array, and we have not covered cell arrays yet. And for that case, what you would do is check the length of this vector. So this variable will always exist. It's a special variable that will contain all the parameters passed into this function. And you can have other variables as input to the function. And the ones that are not captured by the variables that have names will be captured in this special variable that contains all the variables that have no name, all the input arguments that do not correspond to a given name. And then you can check the length of that input argument vector. If it's empty, that means there's no input corresponding to that. If there's one or more, that means you have additional inputs that you can extract. So that's the subject of cell arrays. Any other questions? Okay, so individual questions will move over. They have to sign it. So let's have you sign in to the website also. If you want to see us again this week, can I ask you to quickly go to this page and fill in your name so we know who joined the session today. If you shout out your name, I'll slide it here. Yeah. My office hours is by appointment. I won't be in this week, but the series